guys.
All right.
We don't, we didn't have tables, so we're all doing that.
Hey, what's up?
Elements.
Mhm.
I didn't know the problems in the book.
Yep.
If you prefer me to like, I'll take a picture of it, turn it to PDF, and then turn it in the graphs right below it.
Yeah,
And
yeah.
take a picture of this. Normally I was gonna do a Word, but I did this first.
Okay, yeah, that's fine. As long as it's,
Organized, right?
yeah, as long as it's organized and it's, it's not like, if it's like 2 or 3 documents, I'm okay with that, but I've gotten cases where like they gave me like 20 JPEGs and like that I don't want. And so as long as it's, organized within like one or 2 documents, that's fine with me.
All right. So like, say, it'll be like many JPEGs, but it's all under one file.
Yeah, all under one file.
Okay, that's what you mean. Okay,
Yeah. Mhm.
Yeah, I'll put a ruler and. Yes,
All right, it's 4 o'clock, so let's go ahead and get started today. All right, good afternoon, everyone. How's everyone doing today? Good, good to hear. Hi, Abraham from virtual Zoom. All right. So today the plan is we're going to finish up our lecture notes from Monday, which was I think we just had one more matrix concept to go over, which is eigenvalues and eigenvectors. Okay. And then from there, we're going to start our review on mechanics and strength materials. Okay. And so I know it's a lot of review. And so, we're at the end of week 2 and we're still kind of in the middle of reviewing stuff. But, for this class, it's a unique thing because, what you'll see later on in the class, we'll be doing a lot of it's probably stuff that you've done before in your previous classes, but just applied to a, biological system. And so just making sure we're all reviewed and we're all on the same page, I think is kind of a good thing for this class. Okay. Okay. One thing I forgot to mention last week was that I did post a homework for this class. And so if you go on Canvas, you'll see that there's a homework 1 that's posted. You should have everything that you need to finish it. And so it mostly just covers the anatomy lecture that we covered last Wednesday, and a little bit of the vector stuff that we did on Monday. Okay, so you should have everything that you need, and it's going to be due next Wednesday. Okay, and Monday's a holiday, and so we're not going to have class on Monday because it's Labor Day, and so don't come here, and so don't be on Zoom either because I'm not going to be there. And so after today, the next time we're going to meet is next Wednesday. Okay. Okay, so are there any questions I can answer before we get started today? Okay. All right, so let's go ahead and finish up our lecture notes on matrix stuff. Okay? And we had one more matrix topic that I want to go over, which was eigenvalues and eigenvectors. Okay? And so this was the fifth one. Okay. So you remember the last one we went over on Monday was determinants, which is number 4. Okay. And so this is going to be number 5. All right, so eigenvalues and eigenvectors, I think, at least from my own personal experience, it's something that I knew existed about matrices, but I didn't really understand them for years. And so I think the reason for that is, I think when most people get introduced to eigenvalues and eigenvectors, they're usually in some kind of math class, right? So either some kind of linear algebra class. But from there, you don't really get to see what they're used for or why they're really useful or cool. And so, hopefully introducing it here kind of from an engineering perspective might give you a little bit more context and a little bit more appreciation for what these guys are doing. Okay. Okay. And so the reason, we as engineers were interested in eigenvalues and eigenvectors is that, we as engineers, a lot of times when we're working with mechanical systems, we're often interested in things like maximum stresses, maximum strains, etc. Okay. Okay. And so if we take example from that we might see in this class, right? So we want to see what's the maximum strength inside this bone at this football player is being tackled, right? And what's the direction of that force? Okay. And so normally, if you have kind of a very irregular geometry like that you will see in this class, that's usually very hard to do unless you're doing some kind of simulations or something like that. Okay. But if you utilize eigenvalues and eigenvectors, these actually are tools that you can use to find maximum stresses and strains. Okay. All right, and so to kind of introduce this concept, so let's take kind of a normal matrix vector multiplication, right? Okay, and so let's say that we're going to take a matrix A and we're going to multiply it by a vector X, okay? And so this A here is a matrix. Okay, and this X right here, this is a vector. Right? And so normally when you perform this operation here, it's just basic matrix vector multiplication, you end up with a different vector, right? We'll call that vector Y, okay? And so just as an example, let's say that A is a 3×3, and that X, in order for it to be properly multiplied, is a 3×1, okay? And so we can see here that the inner dimensions here match, okay? And so we can perform this matrix vector product, okay? And then what we get in the end here is a vector Y that's also 3×1, okay? I remember last time that's how we check to make sure that we can perform, any kind of matrix multiplication, okay? All right. And so for most cases, this Y right here, this is different than X, right? And so you multiply a matrix by a vector and you get a different vector in return. Okay. But what if I told you that there are some cases where if you multiply a matrix by a vector, you actually get that same vector back again, okay? Okay. Maybe not the exact same vector, but maybe a scalar multiple of that vector, okay? So what if we have this situation instead? Where this x right here is the same x that's on the left. Okay. And then this lambda right here, this lambda here is just some scalar value. Right? So remember last time we learned that we can multiply a vector by a scalar, and it's going to multiply through all its components, right? So it doesn't modify the size or anything like that. Okay. Right. And so there's very specific situations where this can occur, right? And of course it depends very strongly on what x is and what lambda is. Okay. But for situations where this does occur, this is when we have an eigenvalue and eigenvector. Okay. And in particular, this lambda right here, which are scalar, this is an eigenvalue. Okay. And then this vector x right here, this is our eigenvector. Okay. Okay. And so for a given matrix A, it could be any matrix A, okay? Okay. There usually exists some combination of a eigenvalue and an eigenvector out there that makes this condition true, okay? Okay. And so, an eigenvector and eigenvalue is nothing more than just, the vectors and the values that satisfy this relationship, okay? It's a very unique one where, you get basically a scalar multiple of the same vector that you put in back to you after you perform multiplication, okay? And why is this significant, right? And so, I kind of led off this section by saying that eigenvalues and eigenvectors will tell you, the maximum values of stress and strain and their directions in a body, right? And so in fact, if you solve this, and so let's say that, A right here, let's say that this A represents a state of stress inside a material, okay? Okay. And so it's just an arbitrary state of stress, okay? And so it has all the normal components and the shear components as well, right? If you find the eigenvalues and the eigenvectors of that matrix, right? What that will tell you, or I should say what the eigenvalues will tell you, the eigenvalues will tell you the maximum values of stress, okay? And the eigenvectors will tell you the directions in which those stresses are occurring. Right? Okay. And in fact, this analysis here where you find kind of the maximum, maximum stresses and their directions, it's used a lot in structural mechanics. And probably the name you've probably heard of it before is called principal stresses. Okay. And so the principal stresses are nothing more than just, the eigenvalues of the stress matrix, okay? And then the directions of the principal stresses are given by the eigenvectors, okay? All right. And so, now the question is, how do you actually go about solving for the eigenvalues and eigenvectors? And so, we're not actually going to be doing that in this class because it's kind of really annoying. And actually, in reality, the best way to do it is to use like MATLAB or some kind of computer software. And so that's a little bit beyond the scope of this course. But I think, I just want to introduce this concept to you guys just to have you guys be aware that, this is a tool that can be used out there and why it's important for these kinds of things. Okay. Okay. So any questions on this? Okay. All right. So that's eigenvalues and eigenvectors, right? And so we're not going to solve for them, but just be aware that they exist and that principal stresses are a thing. Okay. All right. And so now let's start reviewing mechanics and strength of materials. Okay. And so this will be kind of like a very quick review of like maybe your statics class and maybe your strength of materials class. I'm actually not sure what they call it here, but when I took it, it was called strength of materials. Okay. Okay. And so now that we have kind of the mathematical background of vectors and matrices that we need for this class, now it's a good idea to kind of review the physics or kind of the physical concepts that kind of drive this biomechanics. Okay. And so in particular, what we're interested in this class, just to kind of peel back a little bit, in this class, we're really interested in analyzing human motion, okay? We're interested in analyzing human motion, and also we're interested in analyzing how the human body responds to external loads. Okay? Okay. And so in order to do these things, especially that second one, we have to have a good grasp of, what are forces and what are internal stresses and things like that, okay? Because it's those things that will tell us, how a muscle will react to, to a force, or how a bone is going to, whether it's going to break or not, okay? And so let's start really basically. And so let's start with just the concept of a force. All right, and so force, intuitively when we think of forces, we think of, as the thing that causes either pushing or pulling that will cause, an object to accelerate, okay? Okay. Mathematically, we represent forces with a vector. Okay, and so they have direction and magnitude. Okay. Right, and so as an example, let me draw my favorite amorphous blob or arbitrary potato, or whatever what you want to call it. Okay, and so let's say that we have an object P. Okay, it's of arbitrary shape, and if we apply a force on this P right here, okay, then what we can say is that this object is going to be pushed with the force P. Or force F, I'm sorry. Okay. And if there's nothing else that's going to hold this object in place, then this force is going to cause this object to accelerate. Okay. And so of course we all know Newton's second law. And so Newton's second law says that the force on an object is equal to its mass times its acceleration, okay? Right, and so what that formula tells us is that, you know, if we apply a force on this object here, it's going to accelerate in the same direction as the force, but proportional to its mass, okay? Okay, so that force is going to cause this acceleration to go that way, okay? Right, and so motion like this, where, you know, a force is being applied into a line, and then the corresponding motion is also a line. This is, we classify this as linear motion. Okay. All right, so pretty simple. You know, we've all kind of seen forces before, but you know, it's just for the sake of completeness. Okay, so any questions on this? Okay. All right, so that's forces. Okay. And so a force is kind of like a linear, you know, like we said, it causes linear motion, but you know, what we'll see is that a lot of motion in the body is actually rotation, right? And so if you take your limb and you rotate it like this, you know, so we have to learn a bit of angular motion as well, okay? And so the angular analog to forces are moments. Okay. Right. And so a moment is kind of like a force, and so it's a you know, it's the agent that causes a rigid body to rotate. Okay. And so in order to compute a moment, you actually need a force, okay? You need a force, and you also need a reference point or a pivot point on which you're going to rotate around, okay? Okay. And so let's say that we have a pivot point O right here, okay? And so let's say that this is you know, what we want to rotate against. And let's say that we have a force vector F, okay? Okay. And then this F is being applied onto the edge of kind of another amorphous blob, okay? Right. And so if this amorphous blob is going to be rotating around point O, the way that we compute the moment for this is that we have to draw a vector, another vector, that goes from the pivot point to where the force is acting on, okay? And we'll call this vector P, okay? And so this P right here, this is a vector that goes from the pivot point to the force, okay? Right, and so with this information, and so if we have this P vector and our F vector, we can compute the moment about O, okay? And so the moment actually is also a vector, okay? And the way that we compute the moment is that we take the cross product between the P vector and the F vector. Okay. And so you notice here that the moment here is a vector, right? And so it's because it's the result of a cross product. And the reason that it's a vector is that, you know, whenever you characterize a moment, you know, the way that you characterize it is, you know, it has to have a certain direction. And the direction of the moment vector is going to be around the pivot around which it's rotating about, okay? And so if you use the right-hand rule that we talked about last time, right? And so if you take your right hand and you take your pointer finger and you point it into the direction of P, and so P here being the first vector in a cross product, and then you rotate your hand around and you point kind of your other three fingers in the direction of F, you'll see that your thumb is going to be pointing into the page, right? And so the direction for this moment vector here is going to be into the page, and that direction tells you around which, we're rotating about. Okay. Okay. So any questions on this so far? Okay. Let's see. Okay. And so, and so you can tell from this that, the location of the pivot point is going to change, how you compute your vectors, right? Or basically where your pivot point is. Oops. And so let's say that we have a situation where, we've computed the moment of a certain force around one pivot point, but then we want to compute the moment around a different pivot point. Okay. Okay. And so this is pretty common, for biomechanical analysis, because, maybe you've computed the moment of, say, you're analyzing an athlete, right? And so this athlete has his foot planted into the ground, right? So he's about to make a cut. And so if you computed the moment of the ground being applied onto the knee joint, okay? But let's say that you want to compute, what's the moment that's being applied onto the hip, right? And so you want to take the moment that you have on the knee, you want to shift its pivot point, and you want to shift it up to the hip, right? And so, one way you can do is you can just simply recompute it from before, or another way you can do is you can take the result that you have already for the knee joint, moment, and then move the pivot point over to the hip. Okay. And so let's say that we have a point O right here, okay? Okay. Right. And so let's say that let's say that we have another point P right here, okay? Right. So let's say that we draw a vector between O and P just like that, okay? Oops. Right. And so let's say that we have a force that goes like this, okay? Okay, and so let's say that we have this normal vector n right here, okay? All right. Right. And so let's say that we want to, instead of finding the moment around O, so let's say that we have the moment around point O right here, okay? If we call this line L, okay, so this line that passes by through O and goes in the n direction, okay? Let's say that instead we want to find the, the moment around this line L, okay? And so the way that we do this is you do a combination of a cross product and a dot product, okay? Okay, and so the moment around line L here is going to be given by P cross F. Okay, and so that's the original moment formula that you have normally, right? And so you have a vector P, sorry, a vector P that points from the origin over to the line of action F, okay? And then what you're going to do is you're going to project this vector onto a line L, okay? And so remember, the way that we project a vector is we use a dot product like that, okay? Oops. Okay. And so by projecting it onto the vector n, then we basically found the component of the moment on that line. Okay. And so in order to keep the result as a vector, then we're going to multiply that whole thing by the vector n as well. Okay. And so with this formula, you're going to be able to basically project any moment from one axis onto another one. Okay. Any questions on this? Okay. Yep. Yeah. So this, sorry, I was a little bit disorganized here. So this n hat right here is a unit vector that points in the same direction as L, right? So L is this kind of dotted line right here. Yeah. So n is just a unit vector that points in whatever direction that you want to compute the moment on. Yeah. Mm-hmm. All right, and so that's moments, okay. And so now that we know about forces and we know about moments, now we're ready to start tackling systems of these, okay. Okay. Because in most practical situations, especially for the human body, if you think about like a joint or you think about a bone, it's not just going to be subject to a single force, right? They're going to be subject to a lot of different forces, right? And so just very simply, if you think about your elbow joint right here, okay? Your elbow joint is subjected to things like the weight of your arm, okay? So it has to support that. But it's also being subjected to all the different tensile forces from the muscles that attach there as well, okay? And so we're going to be dealing with situations that have a lot of different forces on them. Okay. And so if we draw kind of our amorphous blob right here, okay? And so let's say that we have one force F1, we have another force F2, another force F3, F4, F5, okay? And so we might have a situation that looks like this, okay? Let me draw just a pivot point O out here, okay? And so for convenience, a lot of times we want to, we want to basically sum up all these forces, into one, okay? Okay. And so the way that we do this is, since they're all vectors, all we have to do is just simply perform vector addition. Okay. And so the way that we kind of denote this for an arbitrary number of vectors is we use the sigma symbol here. Okay. And so sigma, all it means is just a sum. Okay. And so if we make a summation from n is equal to 1 to big N, where big N here is the number of different forces that we have. Okay. And so in this case, big N would be 5 because we have 5 different forces on this system. Okay. Right. And then what we're summing up here are all the different forces. Okay. And so I'll call them Fn. right? And so if we perform this summation, and then what we get in the end is one single force R. Okay. Where this R, the name that we give this force right here is oftentimes called the resultant force or the net force. Okay. And so this is really convenient because instead of dealing with a lot of different force vectors, and so if you just simply add them all together, you just get one single vector. Okay. All right. So any questions on this? Okay. Right. And so the same thing goes for the moments too. Okay. And so just like we can compute a resultant force, we can also compute a resultant moment as well. Okay. And so, let's say that let's say that each of those forces on the diagram on the previous page is going to be acting on, on the body and causing a moment. Okay. And so the resultant moment about the axis O is given by, okay. Okay. We're going to do a summation of all the individual moments. Okay. Just like that. Okay. Right. And so we'll be doing a lot of this in this class, right? And so, we'll be doing a lot of, we'll be analyzing a system where we're considering different muscle forces, different external forces, and we want to find the external, the total force or the net force, okay? And so kind of for the first, for the first half of the class, or probably up until, maybe around week 9 or 10, we're going to be performing static analysis, okay? And so the way that you perform static analysis is that you simply compute the resultant force and the resultant moment for a given system. Okay. And so this system is going to be comprised of lots of different forces, okay? And so you're going to have to draw a free body diagram. Okay, so drawing a free body diagram will help you a lot because it'll help summarize all the different forces that are there, okay? And then what you're going to do is you're going to set all the forces equal to 0. Okay. And so in fact, I think one of the homework problems I'm having you guys do this. And so I think for the last problem in the homework, I gave you a shoulder joint. Okay. And I told you that, this shoulder joint is being subjected to, I think 3 or 4 different forces from the muscles, as well as an external impact. Okay. And so what I wanted you to do on that homework problem was to compute, what's the resultant force on this. Okay. So you're going to add together all those vectors. And I think in the end, I think you can compute, what's the reaction force at the joint. Okay. And so, this is something that we'll be doing a lot in this class. And so, definitely kind of brush up on your free body diagrams and, and all those stuff. Okay. Any questions on this? Okay. All right. And so let's talk about some special force systems that are out there. Okay. All right. And so these force systems are usually, they're good to know. I mean, you've probably encountered all of these, but by giving them names, it'll make their analysis a little bit easier. Okay. And so first, let's talk about the zero force system. And so we actually just finished talking about it. Okay. Okay. And so the zero force system is one in which there's zero resultant force and zero resultant moment. Okay. Okay. And so in other words, what we can say about zero force systems is that they're in static equilibrium. Okay. Okay. Right. And then this is going to form the basis of our static analysis. Okay. All right. And so now let's talk about couples. Okay. And so a couple is a special force system that has zero resultant force. Okay. Has zero resultant force, but the resultant moment is not zero. Okay. And so what this will tell you is that there's going to be no linear motion, and so the body's not going to translate in space. Okay. Okay. And so it's going to be completely still, but there is going to be angular acceleration here, and so it's going to start to rotate, but it's just not going to move. Okay. Okay. And so visually, if you want to see an example of this, so let's say that we have I guess this one's an avocado, okay? And so we have an avocado, and we're going to put one force on it on this side. Okay, so we'll call this F1, and we'll put another force of equal and opposite magnitude on the other side. Okay, so we'll call this F2. Okay. All right. And so because F1 and F2 have the same magnitude but face in different directions, then this avocado is just not gonna move. Okay. But because the moments are not equal and opposite here, okay. In fact, both of these are going to cause the avocado to rotate in the clockwise direction. Okay. What's going to happen is that this avocado is going to start to spin. Okay. And so this would be the same thing as if you took an avocado and just kind of spun it on your countertop. Okay. Okay. Right. And so a lot of the motion in the, of your limbs can be characterized as couples like this, right? And so if you think about, if you think about moving your arm kind of up and down, then your arm is not, it's not traveling to the other side of the room, but it's only just simply rotating, right? And so the reason it's rotating is because the force system there is a couple, right? So no net force, but there is a net moment on there. Okay, so any questions on this? Okay. All right, and so the last special system that I want to talk about is equivalent force systems. And so equivalent force systems, I would say two force systems are equivalent if they have the same equivalent force and the same equivalent moment. Okay. And so let's say that you have two force systems that are in static equilibrium, right? And so those two force systems are going to be the same, because they have zero resultant force and zero resultant moment. Okay. All right. And so here's where kind of the distinction comes in. Okay. And so if you're talking about rigid bodies, and so if you're thinking about two rigid systems that are equivalent, okay. And so if you have two rigid bodies with equivalent force systems, then their motion will be exactly the same. Okay. Okay. Right. And so if you look at just look at two stationary objects that are in front of you, right? And so on my desk here, I have my glasses and I have my phone, right? And so if they're both just sitting on the countertop, they're both relatively rigid objects, okay? They have zero resultant force, and so both of them are just chilling, they're not moving, okay? But you do get into some differences for deformable bodies, okay? Okay. And so if you have deformable bodies, an equivalent force system does not mean that they're going to deform the same way. Okay. Okay. Because remember, the resultant force is just the sum of all the different forces that are acting on it, okay? But you might have a situation like this, okay? And so let's consider two deformable beams, or I guess these are rods in this case. Okay. And so by deformable, all I mean is that, we consider local deformations of the object, okay? So we don't treat the entire thing as one just kind of rigid thing, okay? And so the extreme example would be something like rubber, right? And so if you stretch a piece of rubber, then the rubber is going to expand, okay? But every object is deformable to some extent, right? And so even if you squeeze like a rock, and you're strong enough, you can actually squish the rock a little bit because it's still technically a deformable body, okay? But of course, there's varying degrees of this. And so let's say that we have two rods, okay? And so let's say that they're made of some kind of soft metal, so maybe copper or something, okay? So I'll draw one rod like this, okay? Another rod like this, okay? And let's say that these two rods are under they have equivalent force systems, okay? Right, and so for the first rod, let's say that it's in static equilibrium, okay? But this static equilibrium is formed by compression, okay? And so let's say that the ends of the rod are being compressed, and we have 10 kilonewtons on each side, okay? Meanwhile, the rod on the bottom is also going to be in static equilibrium, but it's going to be in tension, okay? Okay. And so let's say that, we're stretching the bottom rod, with a tensile force of 5 kilonewtons in each direction, okay? And so in terms of, the resultant force is exactly the same for these two, right? So both of them have zero resultant force, okay? But we know, just from our knowledge of what a deformable model is, we know that the deformation is going to be different, right? And so if we consider the top rod, we know that this rod is going to compress a little bit, right? And so if I draw kind of a prediction of what it would look like, okay? We know that it would deform in a way such that it'll get smaller, okay? Meanwhile, the rod on the bottom, because we're stretching it with tensile forces, we know that this rod's going to get longer, okay? Okay. Right, and so you want to be careful. You want to be careful of this because I think I think the temptation is that, when you have the same resultant force on a system, which for a lot of times is just zero, then you would think that, that they would deform the same way. But, there's lots of different ways to get to zero, right? And so there's lots of different paths that you can take to get to zero resultant force. Right? And so when you're talking about deformable bodies, which we will do for a lot of this class, you want to make sure that you consider, all the forces kind of in their entirety. Okay. And so the resultant force is important just for determining whether you have static equilibrium. But once you have the resultant force, make sure you go back and look at how you got there to actually tell you how the object is going to deform. Okay. Okay. Any questions on this? Okay. All right. And so the reason, the reason why, we have that phenomenon there, and for deformable bodies, is that, whenever you have a deformable body, we have what are called local effects. Okay. Okay. And so maybe the entire object might not be moving, but different parts of the object might be kind of deforming, in response to external forces. Okay. Right. And so there's a very important principle that goes along with this for deformable bodies called Saint Venant's principle. Okay. Did you guys go over Saint Venant's principle in previous classes before? No. Okay. Oh, okay. Cool. It'll be something new then. So Saint Venant's principle is it's not really like a mathematical thing. It's more something to kind of give you some intuition, which I really like, right? And so it's something that you can look at a situation and you can kind of make a prediction kind of based on Saint Venant's principle, which I think are the coolest kinds of principles, right? And it's useful for what we're going to do in this class, but it's actually also really useful for other subjects too. And so actually right after this, I teach a class on finite elements, and this is actually really useful to help you debug finite elements as well. Okay. Okay. And so what Saint Venant's principle states is that in the interchange of equivalent force systems, or equivalent force systems produce different let me start over. All right. So Saint Venant's principle says that, if you have equivalent force systems, we know that we're going to get different deformations, right? Okay. But what Saint Venant's, and so we know that kind of from the previous example, right? But what Saint Venant's principle tells us that, the nature of these differences, or where you see the most differences, are where the forces are being applied, okay? Okay. And so conversely, the kind of the converse of this is that if you look at a region on your object that's far away from where the force is being applied, you can kind of reasonably assume that that area won't really deform that much. Okay. Okay. And so that's kind of a lot of words. And so let's kind of illustrate that with an example. Okay, so let's go back to our two bars from before. Okay. And so we have bar number 1, bar number 2. Okay. And we know that bar number 1 is under compression, right? Okay. Meanwhile, bar number 2 is in tension. I need to clean this up a little bit here. Okay. And so we know from the last page that bar number 1 here is going to be compressed, right? And so they're both sides going to push in, and then the bar is going to become squished, whereas bar number 2 is going to be pulled out and it's going to be stretched out. Okay. And so what St. Venant's principle states is that in these areas over here, at the ends of the bar, okay, right, at the ends of the bar, these are where the force this is where the force is being applied, right? And so this is where you're going to see the biggest differences between the deformation. Okay. Okay. And so if you just look at just the tips, you can see that one is going to be squished in, the other one's going to be stretched out. Okay. But let's look at the region of the bar that's farthest away from the force application. Okay. Okay. And in this case, the region that's farthest away from the areas of force application is right in the middle. Okay. And so if you just look at the middle of these bars, and you kind of just zoom in on both, you probably wouldn't be able to tell one from the other one, because the middle is so far away from kind of where the force is being applied that the middle doesn't really have any changes in deformation between the two. Okay. Okay. Right. And so all St. Venant's principle is saying is that, if you're getting, the farther away that you get from areas of, loading or areas of constraints, right? Then, you kind of, the body kind of loses memory of those loadings, right? And so, the closer you are to the loadings, the more that you feel it, right? But the kind of the farther away that you are from these kind of boundary effects, you're just not going to feel it as much, okay? And so this is a really important, I think this is a really cool principle, because, you can take kind of an arbitrary situation and you can talk about, this area of the model right here is not going, or this area of the structure is not really going to feel any effects, or it's not going to feel any stress because it's far away from all the different loadings, okay? Yeah. And so this is going to be important, once we start to discuss, things like long bones, right? And so we think about things like the, like let's say your femur, which is your thigh bone, right? And so for your thigh bone, a lot of the loads that your thigh bone experiences are going to be at the edges, right? And so they're going to come from reaction forces with your hip or with your knee. They're going to come from the regions where the muscles are tugging on the thigh bone, okay? But in the middle of the thigh bone, there's actually not that much stress over there, okay? And actually, if you look at the structure of a long bone, and we'll go over this, in a couple of weeks too, that bones kind of are thinnest in the middle, right? And so they're kind of thick on the outsides and kind of much thinner in the middle. And part of that reason is the middle doesn't actually experience as much of the stresses or as much of the loads as the ends do, because that's where most of the loading occurs. Right. And so I think the question that a lot of people ask is, how far away do you have to travel from the ends in order for St. Venant's principle to kick in? And 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 unfortunately, there's no precise answer to that. And so St. Venant's principle is not, it's not an equation, and it's not like a formula that you can plug in where you say that, I have to travel this far away in order to not feel the effects anymore. It's more of a conceptual kind of qualitative principle that kind of help you, kind of give you some intuition for how these deformable bodies will deform. Okay. All right. So any questions on this? Okay. All right. And so that's the review for kind of basic mechanics. Okay. So now we're going to start our review of strength of materials. Okay. And so we have about 20 minutes left for today, and so we'll get as far as we can, and then we'll pick this up next Wednesday. Okay. Okay. And so strength of materials, this is a subject which basically defines, or it specifies how an object or a structure will deform in response to external loads. Okay. Okay. And so the way that the way structures deform, it depends a lot on the strength of the material, right? Okay. Right. And so intuitively, we know that if we apply a certain amount of force to a metal object, right? And so let's say you have a metal bar, and you try to bend it like Hulk style, right? You know that it's going to behave a certain way because it's made of metal. But if you took the same bar, or maybe a different bar with the same geometry, but maybe you make it out of cheese or something, right? And you try to take that bar of cheese and you bend it, you know it's going to behave a different way because it's made of a different material. Okay. And so having knowledge of how different materials will deform in response to stress, this is another important concept that we'll go over a lot in biomechanics. Okay. All right, so let's start with just the concept of stress just in general, okay? Because I've been talking about stress a lot, and I think as students, I think you guys have a very different definition of stress, right? But we're going to talk about stress in structural materials. Okay. Okay. All right. And so stress, we kind of have to start with kind of the most basic definition of stress, right? And so stress is nothing more than just a force that's distributed over an area. Okay. Okay. And so the key words here are force and area. Okay. And in fact, this is the exact same definition as pressure, right? Okay. And so in fact, the units are the same as pressure, right? And so the units for stress are going to be force divided by an area. Okay. Okay. And so the SI units for stress are often newtons per meter square. Okay. Which has a special name. It was named after the dude that that found out you can take force and divide it by area. And so these are named pascals. And the symbol we give for that is PA. Right? And actually, the symbol that we give for stress usually is a sigma, or at least the one that I use. And so in terms of dimensions, in terms of units, it's exactly the same as pressure, okay? But the reason, we call it different, or the reason we kind of differentiate it from pressure is that the context in which we use stresses is different than the context in which we use pressures, okay? And so for pressures, pressures, we usually use the term pressure for something that we're, kind of actively or externally applying to a surface, okay? Okay. And so you can say that your professors apply a lot of pressure on you guys in order to when we ask you to do assignments and stuff like that, right? And so stress is something that's more internal to a structure. Okay. Okay. And so stress is something that's experienced internally to a structure that's needed to maintain equilibrium. Okay. And so you can say that, in response to the pressure that you get from your professors, you develop stress inside your brain in order to kind of cope with that. Okay. And so, this distinction is really important because they have the same units. And so I think people get confused between pressure and stress pretty often. And so, dimensionally, they're the exact same thing. It's just the context in which we used and the context in which we use them are different. Okay. Okay. So any questions on this? Okay. All right. And so let me focus on kind of the context for stress, right? So stress, remember, is something that develops internally inside a structure in order to maintain equilibrium. And so if we go back to our rod example, okay? So let's say that we have a rod like this, okay? And we're pulling at it at both sides with some tension T, okay? We know that this rod here is in equilibrium. Okay. The entire rod is in equilibrium. Okay. And so if this entire rod here is in equilibrium, what that means is that if we slice the rod here, okay, and we just kind of took a peek inside, okay, okay, and so we kind of took just a slice of the rod just like that, okay. This slice also has to be in equilibrium, right? And so there has to be some kind of internal forces that develop in order to keep this segment here in equilibrium, because every segment of this rod has to be in equilibrium. Okay. 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 And so in order for that segment to maintain an equilibrium, a stress has to develop on the surface. Right. And so since that surface has some non-zero area, it doesn't make sense for that stabilizing force to be concentrated at a particular point. Okay. And so this stabilizing force is then distributed across the entire surface, right? And so since we have a force that's distributed over a surface, that's why we call it a stress, okay?
Okay. Okay. And so just like just like on the previous page, we'll call this stress sigma. Okay. Right. And so in order to maintain equilibrium for this situation here, okay, if we take this sigma and we multiply it by the cross-sectional area of that cross-section, okay, okay. In order to maintain equilibrium, the product of the stress and the area has to be equal to the tensile force that we're applying on the outside. Okay. Right. And so we can thus use this formula and we can solve for the stress. Okay. And so the stress is going to be nothing more than just the applied tension divided by the area. Right. And so that's kind of a simple way to compute the stresses here in this situation. Right. Any questions on this? Okay. All right. And so let's go over the two different kinds of stresses, or the two different directions for stresses that we can see. Okay. And so one type of stress that we have is a normal stress. Okay. And so a normal stress will act perpendicularly to a surface. Okay. And so the stress that we had on the previous page was a normal stress. Okay. And so the other type of stress that we have is a shear stress. Okay. And so a shear stress will act parallel to the surface. And so if we draw kind of two examples here, okay, so let's say that we have a structure like this, okay, and so a normal stress will act in perpendicularly to this, okay, so we're going to have normal stress that acts this way. Okay, whereas a shear stress is just going to act parallel to this. Okay. All right. And so, we oftentimes we can characterize this stress in terms of, which directions that they go. Okay, so we have normal and shear here, but you can also characterize them in terms of, which Cartesian direction that they go. Okay. And so, the most general case that I can draw here is a cube in 3D space. Okay. Okay. And so this cube here is going to be subjected to, normal stresses and shear stresses. Okay. So let's draw all the normal stresses first. And I'm going to use the same color scheme that I did before. Okay. Okay. And imagine that there's another normal stress going out the back. Okay. We also have shear stresses that are in the plane of this of these cube faces as well. Okay. Okay. And so once you start to get, the X and Y and Z directions involved in here, the stress state starts to get pretty complicated. Okay. And so in fact, there's actually 6 different unique components of stress that takes place on any given object. Okay. Okay. And out of these 6 components, there's going to be 3 normal stresses. And 3 shear stresses. Okay. And I'll write down what these components are on the next page, as well as their definitions. But before we do that, are there any questions on this? Okay. All right. And so the 6 components of stress. And so I think, we'll write these down, we'll define these, and then we'll call it a week. All right, so let's do all the normal stresses first, okay? So first we have sigma xx, and so this is a normal stress in the x direction. Okay. We also have sigma yy. So this is a normal stress in the y direction. Okay. Then we have sigma zz. Sigma zz is a normal stress in the z direction. Normal has 1 L. Okay. All right, so those ones are pretty straightforward, okay? And so now we have the shear stresses, okay? And so the shear stresses are a little bit difficult to kind of, comprehend. So let me go kind of step by step, okay? So first we have tau xy, okay? And so this tau xy, this is a shear stress in the y direction that's on a face that's normal to the x direction. Okay? Let me write that down and I'll kind of show you what I mean by that. All right. And so, let's draw a Cartesian axis here, okay? And so let's say that this is the x direction here, okay? And so this is the y direction. And so let's say that z comes out this way, okay? And so let's start with the back. Let's start with the back part of this definition here. And so let's look at a face that's parallel to the that's perpendicular to the x direction. Sorry, it should be perpendicular. Okay. And so a face that's perpendicular to the x direction would look something like this, okay? Okay. And so as you can imagine, it's something that's kind of turned to the right, okay? Right. And so this face is such that the x direction is pointing normal to it. Okay. And then the shear stress is actually going to be in the plane of this guy pointing up this way. Okay. And so the shear stress is pointing up in the y direction. Okay. And so it's parallel to this face, but the face itself is normal to the x direction. So this is tau yx right here. Okay. And so that's how you kind of interpret those shear stresses. Okay. So it's 5:15, so I think we'll call it here today. And so are there any final questions on this? Okay. All right. So thank you guys for coming today. Thank you guys for tuning in. Remember, Monday is a holiday, so there's going to be no class on Monday. So have a great long weekend. Stay safe out there, and I'll see you guys next Wednesday. Yeah, I can go back. Yep.
Just letting you know, I might be a minute or two late
Uh-huh.
to the next class. I need to go get a coffee because I was like having trouble staying awake.
Okay. Yeah, no problem.
Nothing about the lecture or anything. I just worked out this morning and so I was like writing, but I was like, so I don't want to fall on my keyboard in the next class.
No problem, no problem. All right, see you, Jacob. Yeah. Which page you want?
Yeah, the next part.
Or 12?
Yeah.
Yeah, no class on Monday, Keith. Mhm.
So three normal stress is here.
Yeah, so the three normal stresses that we talked about are actually this one, and this one. And so all the ones that are opposite, we consider them to be kind of the same. And so like if this right here, this is sigma XX, then this is also, since it's also in the X direction, we call that one sigma XX as well. Because remember this whole cube is in static equilibrium. And so in order to oppose this force, there has to be one of equal and opposite on the other side.
So the 6 components is just a 3 plus 3 shear stress.
Exactly. Yeah.
Okay, thank you.
Mhm. Yeah, we'll this will make more sense when we finish it up next week. Yeah. Mhm.